Various geological and geomechanical processes within the subsurface usually induce time-lapse changes within the subsurface or any scattering medium. And these changes are usually weak or localized in space. And we have a lot of studies that have showed effectively how we can use multiple scattered waves to monitor these changes because of the high sensitivity that multiple scattered wave provides compared to single scattered waves because of the redundancy present in the multiple scattered waves. Some of the changes we're interested in monitoring include changes within the subsurface, for example, in a stimulated reservoir, for example, in hydrofracturing activities or production activities where you have effects resulting from fluid migration. We have changes that can be induced. Usually, these changes might be very weak to be monitored using the conventional imaging schemes, such as reflections or direct diving waves. Some other changes can be changes in the near surface due to localized stress change or the effect of groundwater in the near surface. Away from geophysics or geology, you might have, we can use multiple scattered waves to monitor changes in mechanical structures due to wear and tear. A lot of demonstrations have shown you can even use it in medical imaging. But before I go on, I would like to step back to the result I presented last year. In our study last year, we showed how effectively we were able to identify consistent velocity change within the subsurface beneath Utah, demarcated by the white line, and some other neighboring states. We were using a subset of the US array that was that Bob from Irish talked about the day before yesterday. We use the active time-lapse experiments to monitor these weak changes within the subsurface by the data shown there with series of multiples that were recorded in our sets of sources and receivers. The idea was to look at the differences in the waveforms and measure time-lapse changes that may be very small, in the order of 0.1%. But the problem we had in our presentation last year was we had little to say about where these changes are coming from within the subsurface. So for time-lapse monitoring, our interest is not only to identify changes, but also to say accurately where these changes are originating from within the subsurface. So for my presentation today, I'll be focusing on localizing weak changes. This can be velocity changes, changes in impedance of your scattering medium. And to do this, we are using this major two imaging equation. The first was developed by Pacheco and Snyder in 2005 using the framework of Coda wave interferometry. I'd like to point out at this point that I'll be interchanging multiple scattered waves and Coda waves. Basically, for the context of our talk today, this just means the same thing. So the first question relates travel time changes to changes in the fractional velocity change within the medium. While in the second equation, you relate the decorrelation between the time-lapse changes to changes in the scattering cross-section of your scattering medium, sigma. So for our imaging problem, we have two data available to us. The change in the travel time of the time-lapse scattered waves, tau, and also the decorrelation. The decorrelation mathematically is just 1 minus the maximum cross correlation of your time-lapse scattered waves. But intuitively, just say something about the differences in the time-lapse signal. And these differences can be differences in the amplitude or the differences in the travel time phase information in the scattered waves. And the decorrelation, so for these two equations gives us two different information about our scattering medium. For the first equation, we're interested in monitoring fractional velocity change within the subsurface, while the second equation monitors change in the scattering cross-section. And for in our context, this can be effects of induced fractures or changes in the porosity within the scattering medium. But the interesting thing about these two equations is that the fundamental Fisher derivative or the sensitivity kernel K is the same for these two equations. So what we just need is to compute the sensitivity kernel for our scattering model and use any of these two equations for the imaging process. Except for the second equation, we are multiplying an additional factor, the average velocity change, average velocity divided by 2. And the sensitivity kernel is given by this equation, which is has two, the numerator and the denominator. The numerator is a convolution of the normalized intensity from a source location to a certain location X we're interested in, and with intensity from that location X to the receiver location. They will normalize it by the intensity from the source location to the receiver location. I like to say that we are using intensity because it allows us to simplify the description, the relationship between the scattered waves with the localized changes we're interested in monitoring. The normalized intensity is just the normalized square of the envelope of our scattered wave field. So this intensity contains all the scattered contributions, both the first, the direct arrival and high order multiple scattering that is present in our data. Recent studies have been using, I started using this scheme to do imaging, especially in global seismology. Most of the interest has been in monitoring time-lapse properties of volcanoes to be able to understand the activities over time. But most of the studies that have adopted this approach compute the sensitivity kernel by the scheme I'm going to introduce at this point. Let's assume that we have a scattering medium. We probe this medium with a series of source and receiver networks. We compute an average scattered waves using our source and receiver array, which contains all the contributions that we're interested in. From this scattered waveform, we can compute the scattered intensity. Then we fit the scattered intensity by a theoretical model, a model that we expect to explain our scattering medium. And this scattering intensity is controlled by a series of scattering parameters. Usually, this scattering parameters gives you an average description of your scattering medium. And from these scattering parameters, we can now compute the sensitivity kernel we're interested in, using the same theory that was used to fit the scattering scattering waveform, the multiple wave encoder. But there is problem, two major problems that is obvious to us using this scheme. One is a long and tedious process. Usually we make assumptions at every level of the process. Secondly, most the scattering parameters you obtain are usually an average description of the scattering medium, which assumes that our heterogeneous medium is homogeneous in nature. This becomes a problem if we have a really complicated medium, especially in the subsurface, where it might have different layers with different scattering characteristics. So for our problem, we are proposing a way to compute this sensitivity kernel directly from our scattering model. What this does for us is that we can compute the sensitivity kernel for any arbitrary scattering model, no matter how complicated this model is. The only assumption we make is that we have a good description of our initial model to compute the sensitivity kernel. Let's go back to our equation for the sensitivity kernel. It turns out that the numerator involves the convolution of the scattered intensity generated at the source location with the intensity generated at the receiver location. They will normalize it by the intensity from the source to the receiver location. Here's an example of a scattered intensity we generate with a simple model. This model, I'll show it later on in the talk. This contains all the scattered phases, both from direct arrival to higher order levels of scattering. They will generate scattered intensity at another location, which is our receiver location. To compute our sensitivity kernel, what we need is just to convolve these two intensities and then normalize by intensity from the source to the receiver location. What do we need to compute the sensitivity kernel? As in most geophysical process, we need a background model. This can be a background velocity model or background impedance model. or this can be a very smooth velocity model with velocity models with layers. Also, we need to use the appropriate physics. If we have attenuation and isotope, we need to include that in our process. I also need other information like source receiver locations, the accurate bandwidth to compute. But the additional requirement for our problem is the need for the statistical property of the scattering model. And I would like to stress that we need the statistical properties of the scattering model, not the macroscopic locations of our scatterers in our scattering model. This is important. This is because we are using the intensity rather than the wave field itself for our monitoring. I'll talk about this later on in the talk. To demonstrate how these sensitivity kernels look, I'll do that using a simple numerical example. For this problem, I'll be imposing my scattering properties on the velocity, keeping my density constant. This is not an assumption that is embedded in the theory, but this is just so for this problem to simplify our problem for now. So this is a simple example I used to generate the intensity I showed earlier on. So I'll be showing the behavior of the kernel using this problem. And I'll be showing that for this source and receiver location. The R is the receiver and the S is the source. So here is the sensitivity kernel at the time of the direct arrival for this simple model. And what you see is that most of the contribution for the direct arrival comes just along the line between the source and the receiver, which this is intuitively. But as you go later on in time, you have a special broadening of the kernel in space, and this kernel is bound by what I call the kernel front, which is dominated by contributions from single scattering. But within the kernel, we have contributions from high order levels of scattering, which constitute the decoder part of our wave from the multiple scattering. And this special broadening of the kernel continues with increase in travel time. But you see additional features in our sensitivity kernel by in the locations of the source and the receiver, where you have elevated sensitivities at these locations. This is because for multiple scatters recorded at this source and source receiver line, most of the contributions come from the near source and the near receiver location. This you see clearly as you go also later on in travel time. At this point, I'd like to point out, because our focus is to use this sensitivity kernel to do imaging, to image weak changes within the subsurface. Comparing the different properties of the sensitivity kernel over different times, what you expect is that earlier on in time, because of the special broadening of the kernel, you expect to have higher resolution for early travel times and lower resolution for late travel times. But the flip side to the story is that for changes that are away from our source receiver line, we expect to identify those changes later on in the decoder, because we have this the scattered wave going through those changes that are away from the direct line between the source and the receiver. Earlier I talked about, like, for our scattered model, we need the statistical property of this scattering medium, and this is important for the stability of the sensitivity kernel. I'm going to compare the sensitivity kernel computed by different realizations of the scattering model, but each of these models we use have the same statistical properties. They are computed with the same statistical parameters. Here is the kernel with one realization of the scattering model. Here is with 5 realization of the scattering model, and here is with 10 realization of the scattering model. What you see is that you tend to stabilize the sensitivity kernel with higher realizations of the scattering model, and we're able to achieve this for a few realization of the scattering model, because there's just little difference between 5 and 10 realizations of the scattering model. So in the next part of the talk, I'll dive into using this sensitivity kernel for our imaging process. And I'll be doing this by using a simple numerical example. What I'd like to focus on this model is that let's consider a scenario where we have a highly fractured horizon within our subsurface. And this is depicted in this figure in the middle layer, defined by the vertical lines, velocity changes. And this horizon might be considered as a stimulated reservoir or horizon within the subsurface, and the stimulation might generate a series of microseismic events depicted by the green circles, which acts as sources for scattered wave fields. And we monitor these changes using two vertical receiver arrays, which can depict the two boreholes for the monitoring process. Our goal is to monitor a velocity change that's embedded within the middle layer. Here we impose a very small velocity change of 0.5%. I'll be showing you some results in imaging these changes. But to solve this problem, we'll be using our first equation, the first imaging equation I introduced, which relates the travel time change to the fractional change in the velocity. I'll be computing this travel time change from two different sections of our time-lapse scattered data. So here is the time-lapse scattered waveforms to compute from that model, and it will generate an average velocity change, travel time change from the black rectangle, which I call the early part of the coda, and the red rectangle, which I call the late part of the coda. And what you see from the image results is that for the early part of the coda, you see that we were able to image the location of the change with slight deviation. The black rectangle shows you the original location of the change. And I would also like you to remember that the magnitude of the velocity change is 0.5%. But in the later part of the coda, this is the result we get. And what happens is that our image change is smeared within the middle layer because of this spatial broadening of the kernel, which reduces the resolution we obtain for velocity, image velocity change. But the interesting thing is that we seem to have a better understanding of the amplitude of the velocity change that is original in our model because of the higher sensitivity that is present later on in the coda, in the scattered waves. We also were able to demonstrate, use our scheme in a laboratory experiment, imaging a change in a laboratory experiment. And for this problem, we had a laboratory setup where we applied stress loading on the surface of this concrete block at the location of defined by the pipe. And we monitor the scattered waves over a series of stress steps. I'll be showing results for stress step of 5 to 10 kilonewton and 5 to 15 kilonewton, just to compare our ability to image these changes and the magnitudes we get. And we monitor the scattered waves using 10 sensors, which one acts as a source at various times. Here's the details of the source sensor locations relative to the location of the applied stress defined by the black X. So for this problem, I'll be using the second part of our equation for our imaging, the decorrelation. I'm using the decorrelation rather than the travel time change, because we observed that looking at our time-lapse coda wave, that the difference was more on the amplitude rather than the phase. So the decorrelation, which measures the differences in the time-lapse scattered waves, contains the information in the change in the amplitude and also change in the phase. So, and for our problem, we can compute this decorrelation for any part of the scattered waves. But for this presentation, I'll be just showing results from this specific time window defined by the black rectangle. So here is the average decorrelation computed for that specific time window for the two stress steps I was talking about initially. The colored lines for the colored line just shows you the average decorrelation for each sensor pairs for the two stress tests. And what you observe is that just looking at the data, you see higher decorrelation, higher differences in the data for higher stress tests, which is intuitive. And also you have the higher decorrelation close to the location where you have where the original stress was applied. And this you see from our image results. The X location just gives you the original location where the initial stress was applied. And we're able to image closely enough the location where the stress were applied originally in our model. And what you see is that you have higher measure of the change in the scattering cross-section, because that's the information obtained from the decorrelation for higher stress depth compared to lower stress depth. So I would like to point out that most studies that have used scattered waves or coded waves have focused on identifying changes rather than localizing or imaging where these changes are coming from. And to do this, I'm able to show that we can use the scattered waves to accurately position the location, the changes we are monitoring coming from the subsurface. So, but for us to do this, we need to have an accurate description of the scattering waveforms we are recording. And this can be achieved by using the scheme I presented using the our algorithm, and also using the computation of the sensitivity kernel that allows us to compute the sensitivity kernel for any arbitrary medium without making assumption of the homogeneous characteristics of our scattering medium. At this point, I would like to thank the Department of Energy for providing some of the funds for this project, and BAM for providing us the laboratory data we use for our test. Thank you all for listening to me and open the floor for questions.